We all take our air conditioners for granted. They pump heat out of a room, but they use a ton of electricity and, frankly, some pretty nasty chemicals to get the job done. But what if we could just flip that whole process on its head? What if we could actually use heat itself to create cold? Well, that's exactly what we're going to explore. The science of adsorption heat transformation, a technology that literally uses heat to make things cold. And this isn't just some neat technical puzzle, right? It's a critical question for our future. Our demand for cooling is absolutely exploding all over the world, but the way we do it right now, well, it comes with some really serious environmental and social costs. So here's our game plan. We're going to start by breaking down the problem with our current cooling methods. Then we'll dive into the incredible science of making cold from heat. We'll take a look inside an absorption chiller, explore the amazing materials that make it all possible, and finally, ask what all this could mean for the future of cooling.
Okay, so let's start with the big why. Why do we even need to be having this conversation? Turns out our go-to technology for refrigeration is surprisingly problematic.
The conventional systems in most of our homes, they're called vapor compression refrigeration systems, are absolute energy hogs. They run on electricity, which, let's be honest, mostly comes from burning fossil fuels. And the refrigerants they use, things like CFCs and HCFCs, yeah, those are the chemicals famous for damaging the ozone layer. And on top of all that, they are completely dependent on a stable electrical grid. And that right there is the crucial point. For huge parts of the world, especially rural communities, reliable electricity just isn't a thing. And that means no refrigeration for life-saving vaccines, no way to preserve food. It has a massive impact on people's health and local economies. This isn't just an inconvenience, it is a fundamental barrier to development. But this is where a truly revolutionary idea comes into play. Instead of using electricity to power a compressor, what if we used a heat source? Something like, say, the sun, or even just the waste heat pouring out of a factory to generate cold. The process is called adsorption heat transformation, or AHT for short. It's an eco-friendly technology that uses a totally natural physical process to create a cooling effect. And you want to know the best part? It can run on low-grade heat, the kind of heat that's all around us, and that we usually just waste.
The core concept here is actually brilliantly simple. Just think of a special, super dry sponge. So on the left, you see this sponge. It's called an adsorbent, and it aggressively pulls in water vapor. This creates a really low pressure environment, which forces liquid water in another chamber to evaporate like crazy. And just like sweat cooling your skin, this rapid evaporation pulls heat from its surroundings, creating a powerful cooling effect. Then, on the right, once the sponge is saturated, you just apply heat to wring it out, driving off the water vapor so it's ready to go for the next cooling cycle. It's a continuous loop. Absorb vapor to get cold, use heat to get dry again. Simple as that. So how do you take that really cool principle and turn it into a working machine? Well, let's take a look at the anatomy of a real absorption chiller. This is what one looks like out in the real world. Now, it might look a little complex, but compared to a conventional system, it is remarkably simple on the inside. There's no loud compressor humming away, which means these machines are super quiet, they don't vibrate much, and they are incredibly durable. And this diagram shows you the internal flow perfectly. To get continuous cooling, you usually have at least two of those sponges, or absorber beds. So while one absorber is in its cooling phase, soaking up vapor from the evaporator, the other one is in its regeneration phase. It's being heated up to release its vapor to the condenser. A series of valves just automatically switches between them, so the cooling never has to stop. Now, to measure how well these systems work, we use a metric called the coefficient of performance, or COP. Really, it's just a simple ratio. How much useful cooling do you get out for the amount of heat energy you have to put in to recharge the material? And this brings us to the technology's biggest hurdle right now. The COP for many current adsorption systems is, honestly, still pretty low, often below 1. So what this means is, while they use a different type of energy, they aren't always as efficient as the traditional systems they're trying to replace. Improving that COP, well, that's the holy grail for researchers in this field. So how do we boost that efficiency? How do we raise the COP? Well, the secret isn't really in the machinery. It's in the sponge itself. The performance of the entire system hinges on that adsorbent material. There are 3 main families of materials being used right now. You've got silica gel, yep, the same stuff in those little do-not-eat packets, which is cheap and stable, but it just doesn't hold much water. Then you have zeolites. They're better. They hold more water, but they really love water, so it takes a lot of heat to get them to let it go again. And then there are moths. Metal organic frameworks. These are the real game changers. They can be engineered to have insane surface areas, hold a phenomenal amount of water, and their properties can be precisely tuned for the job. This quote from the research really nails it. That phrase, designable pore structures, that's the key. Imagine being able to design a material's internal architecture at the atomic level, literally creating custom-shaped pores that are perfectly sized to grab onto water molecules at one temperature and then just let them go at another. That's the power of MOFs. It's less about finding a material and more about designing one for the exact job you need it to do. But look, having a high capacity isn't enough. The really crucial challenge is durability. The material has to be hydrothermally stable, which is just a fancy way of saying it has to survive being constantly heated and soaked with water vapor, over and over without breaking down. For a commercial chiller, we're talking about over 100,000 cycles. That's a 10-year lifetime. So finding a material that's both super high-performing and incredibly tough, that's the key challenge. Okay, so when we put this clever cycle together with these advanced materials, where can this technology actually make a real difference out in the world? The applications are just incredibly inspiring. On the left, you're looking at a solar-powered adsorption ice maker, providing crucial refrigeration to preserve food in a remote village that has no electrical grid. And on the right, that's a disposable cooling box that uses this same principle to keep life-saving vaccines at a perfect temperature for days, no matter how hot it gets outside. No power required. And when you zoom out, the system-level impacts are profound. This technology can turn industrial waste heat from a problem into a valuable resource. It can run directly off of solar thermal panels. It often uses plain old water as its refrigerant, which is completely harmless. It reduces our dependency on the grid and brings essential services to places that have been left behind for far too long. Of course, we're not quite there yet. There are still hurdles. Researchers are working hard to improve the long-term stability of these amazing materials, to simplify the system designs, to make them even more robust, and, most importantly, to bring down the manufacturing costs so this technology can compete head-to-head with what we've got now. But the potential is absolutely undeniable. It really forces us to ask a powerful question. As our world keeps getting hotter, could the heat we currently just throw away actually become the very thing that helps us stay cool, both sustainably and equitably? The answer might just be locked inside a tiny, porous crystal.